Hi, I'm Siddharth and I'll be showing a brief demo of Workbench, a low-cost numerical simulation and real-time prototyping platform that we developed at the University of Minnesota as a part of our ONR-funded project as a replacement to previously used MATLAB DSpace combination. Workbench is similar to other model-based design environments such as MATLAB, Plexim, PSIM, etc., allowing users to develop complex algorithms using pre-built drag-and-drop toolboxes. In this example, a simple sine PWM of 3-phase 2-level inverter is shown. A 60 Hz 3-phase reference sine wave centered around 0.5 is compared with a sawtooth carrier of 1 kHz. The output is the gate on-off pulses for the inverter. One of the interesting features of Workbench is to anticipate runtime error before running the model as seen here. It can identify arithmetic loop errors, data type and size mismatches, etc. as soon as they occur rather than wait till runtime, which helps immensely in debugging and speeding up the design. The result of running this model in simulation mode can be seen in the scope showing one of the inverter legs gate signal. In the following demo, we shall explore a much more complex system of induction motor vector control. Here is the overall view of the model. On the top is the linearized induction motor model, which consists of multiple subsystems within it. And in the bottom is the DC motor model, which emulates the load. The DC motor is run in torque control mode to emulate a step load to ensure that the motor speed is maintained constant. The induction motor is operated in speed control mode with an inner current loop to maintain the motor flux and torque and an outer speed loop. The PA values are calculated in the script file seen here, which is similar to M file in MATLAB. Running the script computes these parameters as well as the d-axis current, torque, constant, etc. The result can be seen in the data peak window on the right. As seen here, the motor speed is stepped from 0 to 100 radians per second at time equal to 1 second, and the torque is stepped from 0 to 0.75 Newton meter at 3 seconds. The flux axis current is maintained a constant of 1.1 ampere determined in the script file. The motor voltage is controlled by the inner current PI loops, and in simulation the motor current and speed is determined by solving the motor model. In real-time control, where an actual motor needs to be controlled, the control code is imported automatically by the software without any additional coding from the user end. The current and speed is determined by reading the values of ADC and AQB toolboxes, for which code is auto-generated. The result of running vector control algorithm in real time is shown here, and the data is logged in the scope as seen. This can be compared with simulation results by dynamically swapping in and out simulation in real-time mode. As per the setting, the motor speed steps from rest to 100 radians per second at about 1 second and remains there in spite of a step load at 3 seconds. The simulation and real-time result match closely as can be seen here. The motor flux axis current is a constant 1.1 ampere and the torque axis current remains close to 0 till 3 seconds, at which point it rises proportional to the load torque so that the speed can remain a constant. The final plot shows the DC motor torque versus induction motor estimated torque. The slight discrepancy in real-time result is due to frictional losses which aren't accounted for in simulation model. That concludes the short demo on Workbench. Thank you.